Today we'll have a continuation for our topic, thermal stress. We answered up to number 3 last time, so let's continue today with number 4. So number 4, please ready your calculator for faster solving. At a temperature of 80 degrees Celsius, a steel tire 12 millimeters thick and 90 millimeters wide that is to be shrunk onto a locomotive driving wheel 2 meters in diameter just fits over the wheel, which is at a temperature of 25 degrees Celsius. Determine the contact pressure between the tire and the wheel after the assembly cools to 25. Neglect the deformation of the wheel caused by the pressure of the tire. Assume alpha 11.7 micrometer per meter degree Celsius and modulus of elasticity 200 GPa. So first, let's analyze what's happening here. We have a tire and a wheel. Your tire is at 80, your wheel is at 25. So your tire will experience a decrease in temperature, hence it will shrink onto your wheel. Now the question is, what is the resulting pressure from the contact between your tire and the wheel? Okay, so looking for pressure. Let's start with writing the given. First, temperature of 80 degrees Celsius, let's call that your initial temperature. So Ti. Next, steel tire 12 millimeters thick, 90 millimeters wide. So T for thickness, 12 millimeters. And then I'll call W your width, 90 millimeters. Just fits over the wheel. And your wheel is 2 meters. So just fits, that means they basically have the same diameter. So diameter of both wheel and tire, let's just call that D, 2 meters. Okay? And then final temperature, 25 degrees. So let's just call that TF. Okay, and then you're given properties of your steel, 11.7 and 200. And then again, for steel, it's always just 200 GPa. Okay, that's your given. Now let's try drawing what's happening over here. So let's say this is your tire. Okay, there. So we have your tire now. Again, with the diameter of 2, inner diameter. So we'll follow the steps for thermal deformation or thermal stress, where we release constraints and we let your object deform. So since your tire undergoes a decrease in temperature from 80 to 25, it will shrink, okay? And the manner in which it will shrink is this way. So it will have a decrease in diameter. So let's say around that, okay? So now that is the final inner diameter of your wheel, okay? So we can call this your deformation due to temperature. And I'll call that delta T, okay? And then the next step in your thermal stress guide is to put it back to its original position using a restoring force. So that restoring force is actually the pressure acting on the tire. So P, or restoring force, capital P. So this diameter will go back to this original position. So the change in diameter would be this. Okay? And that I'll call that your delta P for restoring force. Okay? So now we have this figure. The next step after drawing your deformations and such is to create an equation relating all of your deformation. So now can anybody give me an equation relating these two variables? Correct verse. Very good. Anyone else? And correct Jan. Verse Guico. As you can see, the amount changed by your temperature is the same by your restoring force. So simply delta P equals delta T. And delta P, you have two choices, right? PL over AE or sigma L over E. Typically, you use sigma L over E if you want to look for stress. We're not looking for stress, so the more appropriate equation to use is PL over AE. Okay, and then for deformation due to temperature or thermal strain, that's just alpha L change in P. Okay, next, let's plug in our values. P, we don't know P, so let's just write that P. P is the restoring force. L, now for the past few examples, L is simply the linear length in which your object lengthens or contracts. Now, our object isn't linear, it's in a circle. So what's actually changing is not length L, but rather perimeter or diameter. Now, lucky for us, the original length for deformation due to restoring force and temperature are the same. So you don't even have to think about it. You can just cancel it out already. Okay? So now you're left with P in the numerator. And then over AE, A is simply the cross-sectional area perpendicular to the length in which your object deforms. Okay? So can anybody give me what that area is? Okay, I'll give you a clue. Let's draw a cross-section of this tire. Okay. So consider this the cross-section. This is your tire. Okay? There. And then along this length is how it contracts and expands. So therefore, this is actually the cross-sectional area that we're looking for, right? So knowing that, can anybody give me what is the equation of that cross-sectional area? Correct, Nicole. Very good. Anyone else? Correct, Chloe. Very good. Macro. Okay. It's simply base times height, or based on what we used here, it's thickness times width. So as you can see, the cross-section is that of a rectangle, right? With base equal the thickness or width, rather the width of your wheel, which is given as 90. And then height of this rectangle is simply the thickness of your wheel, which is 12. So this is 90 times 12. And then E, 200, convert that into MPa. So 200 times 10 raised to 3. Okay? And then equate that to this. Okay. Alpha given 11.7. Now look, it's micrometer. We already know when you have a micrometer per meter, just multiply by times 10 raised to negative 6 to convert micrometer to meter. Okay? Again, L canceled out. Change in T given. Final temperature, 25, initial 80. Now, this gives you a negative answer. However, remember, since we already accounted for the shrinking and expanding of your material, you can simply just get the magnitude instead of your thermal deformation. So just add an absolute value here. And then from this, you can solve what's P. Correct, Mariah, Cavero, who else? And Verse. Very good. 138,996 Newton. Okay, so that's force. That what we solved for is the restoring force. Okay? We're not looking for that. We're looking for pressure. Remember? So now I need to know or figure out how to relate this restoring force to pressure. Now let's focus on this restoring force. Another way to look at this restoring force is it's the force giving stress to your tire. Okay? So it's the internal force creating stress in your tire. Now your tire is a cylindrical vessel, technically. Okay? So you can analyze it as that. And remember, for a cross-section of a thin-walled cylinder, the force that is present along the cross-section is your restoring force, or also known as the force that results from the stress on the material of your cylinder due to the pressure inside the cylinder. Okay? So they're the same. This P is the same as the P that you see here. Okay? In the past, we called this T, I believe, because it's a tensile restoring force. But now it's P because it's the same. It's the force from the stress being experienced by your material. Okay? And then again, this force is resisting the force due to pressure, which is your F. Okay? And now we have your free body diagram, typically for your thin wall cylinders. From this, remember, we can create an equilibrium equation. Summation of forces equals 0, right? So let's say F minus 2P equals 0. So F equals 2P. Now, F, again, is the force due to pressure in your cylinder. In our case, this is force due to pressure between your tire and the wheel. So they're the same. It's still pressure. And this F is taken because it's the pressure acting on a projected area. So recall pressure is force over area. Force, therefore, is pressure times area. And once again, that area is your projected area. So PA. Okay, let's distinguish small p, pressure, capital P, what we solved for here. Okay, and then let's solve P. Again, A, projected area, which is simply a rectangle once again, with base 90, and then height equal to this, which is the diameter of your tire, and that diameter is 2 meters. Our units are in millimeters, so convert that to millimeter. So P times 90 times 2,000. Okay, equals to whatever we have here. That's 138,996. And then from this, you can solve for pressure. Please solve. What's the answer? Correct, Jan and Ralph. Bansilwico. Right, it's 1.54. And that's it for problem number 4. Do you have any questions for number 4? Please answer in the chat. No questions? Great. Let's have number 5. Okay, number 5. A rigid horizontal bar of negligible mass is connected to 2 rods as shown in the figure. If the system is initially stress-free, calculate the temperature change that will cause a tensile stress of 90 MPa in the brass rod. Assume that both rods are subjected to the change in temperature. Okay, again, analyzing. So there's no applied force in this system, bar and rod. Okay, however, there will be a temperature change, and we want to know what that temperature change is to cause a tensile stress of 90 MPa in the brass rod. Okay, so let's write that. Tensile stress, I'll call that sigma BR, 90 MPa And then let's specify that as a tensile stress. Okay. All right. So to approach questions like this, in the past, you've noticed all of our questions don't involve this kind of system. It's just a tire, it's just rods, there's no combinations, just rails, again, rod. Now, if you have something like this, it's ideal or more practical to start with a free body diagram to figure out the internal forces in your members. In our case, in the rods. Okay, so let's start with a free body diagram. Okay, and then these are rods. Now remember, rods, cables, ropes, etc. all carry tensile force. So you must draw your vectors in such a way that represents tensile force. So that's away from your member. So let's call this PBR, okay, internal force in brass, and then I'll specify that again as tension. And this is also a rod. So again, away. And then this is your PCU for copper, and again, let's specify that as tension. And then this is 3, this is 2. Now the next step is to create your equilibrium equations because you have a free body diagram. So let's call this, let's say this is a pin connection, pin support, call that A. Now again, we'll create an equilibrium equation. You have 3. You have forces vertical, forces horizontal equals 0, and moment. Which of those 3 should I use here? Can anyone tell me? Very good, Tristan. It's moment. Okay. Also John, correct. Be honest. So it's moment. Why? Remember, for supports, always in any situation or in simple setups, there's always reactions there. So this is a pin. So there's possibly a vertical and horizontal reaction. Now I don't want to solve that. That's an additional unknown. So instead of using vertical horizontal equals 0, which will include those two, I'll use summation of moment at A equals 0. So then AVAH will just not be included in the equation anymore. Okay? Typically, moment is the equation to use. Now let's solve. Starting with PCU, rotate about A, that's clockwise. Therefore, positive PCU, perpendicular distance 3. Next, PBR, rotate about A, that's counterclockwise, negative PBR, perpendicular distance 5, equals 0. Now take note, what we're looking for is stress, right? What we're looking for is temperature change. However, what we are given is stress. So I'll rewrite this equation to include stress so that I can use this given. Once again, P is simply stress times area. So stress CU times area CU for copper times 3 minus stress bronze, brass rather, times 5. And then let's sub. We don't know stress in copper. Area in copper, however, is given. What is that? 1,500 millimeters squared. Okay. And then times 3 minus stress in brass given 90. So minus 90. Area of brass also given 1,200. So 1,200 times 5 equals 0. From this, we can solve for stress in copper. Please solve. What's the answer? Correct, Christian and Tristan. Denaga de los Reyes. It's 120. 120 MPa. Now we have both stress for brass, and for copper. Now, what's the importance of that? Well, recall, what we need to get deformation due to restoring force is simply stress, length, and area, all of which we already have. So we can already solve for deformation here. So we can start with that. Stress in brass, that's stress BR L BR over E, right? Stress BR given 90. Length of brass also given 2 meters. Again, units are in millimeter, so convert times 1,000 or times 10 raised to 3. Okay, and then over E, which is 100. So 100 times 10 raised to 3. What's the answer? Please solve. Correct, Jan. And who else? Gwyneth. Correct. Rico. And the Guzman. It's 1.8 millimeter. And then, likewise, we can get deformation in copper. So once again, that's stress copper, length copper, E copper. We solve for that, that's 120. 120, length of copper also given 3 meters, so that's 3,000 millimeter, all over modulus of elasticity, which is 120 GPa, times, again, convert to MPa, times 10 raised to 3. I don't even need a calculator here, that's just 3. Yeah. Right? Can cancel out 120, 1,000, 3. Okay. So now I have all of these deformation, right? So this deformation relates to deformation due to restoring force. Okay? That restoring force is one of the last steps we had in thermal stress. So this is not total deformation accounting for temperature and force. Okay? No, it's just deformation due to restoring force. Okay? So let's differentiate. So we have deformation due to applied force. For example, here, this is an applied force. This is deformation due to applied force. And then we also have a deformation due to temperature. And then finally, we have deformation due to the restoring force, putting it back to its final position. In this case, final position is here because your rod is attached to a wall. So even though there's a change in temperature, the ending dimension is still up to here only. So that's why this is your deformation due to restoring force. Okay, so it's not immediately the total deformation of your system, right? So now we know that deformation due to restoring force. Now the next step is to account how will this deform. Okay, now we need to draw a free body diagram to support the steps in thermal strain. So in order to do that, let's consider what type of forces and hence stresses are being experienced by rods. They're both in tension. So my bar should move in such a way that my copper and brass will both be in tension. So there's only two ways this bar can move. Okay, I'll show you. So this is your bar, right? This is, again, a pin. When you have a pin, your beam, rod, bar, whatever, can rotate. It's free to rotate. Okay? That's why there's no moment support here. Now, this can either rotate this way or it can rotate this way, depending on how your rods deform. Again, they should be in tension. Now, let's assume it rotates this way, right? Now take note, your rods should deform in such a way that, again, it's in tension. So let's draw its original position. Okay, so let's say this happens when this rod shrinks, okay, and then this rod expands, you'll have this. But remember, your brass and copper can only experience one type of change in temperature, right? So instead, let's say, okay, so your rod will, let's say we have a positive change in temperature. Okay, so your rods will expand, and let's say it will end up here. So what will happen there is, if it's gonna expand, let's say, yeah, this is your expanded rod, and we're assuming it ends up here. There. Okay? Now the restoring force will force or will push or pull the rods to this final position, because that is where we assumed your bar to rotate. So that means this bar will uh, compress. Same thing here. This bar will compress, which is the opposite of what we want. They should be in tension. So that's not the case. We don't have a positive change in temperature. Okay? Another thing, okay, so we already know this is incorrect. Our bar won't transform this way. So it's the opposite, right? Because again, if your bar ends up this way, restoring force will make your bar compress. Should be in tension. Okay, so now we know that. So this is the final position of your bar. There. Okay. All right. So now that that's established, the next question is the change in temperature positive or negative? Are your bars shrinking or expanding? Again, we can test for both and check, will that create a tensile stress in both the bars? So again, let's check positive change in temperature. Okay. So let's say your, again, starting point of your bar is over here. Okay. It's always the same. Again, same thing here. Starting point of your bar is over here. And then positive change in temperature. So let's say it expanded to this point. Okay, let's just assume, right? So that we can say the restoring force will push it here. Hence, this bar is in tension. Okay, so check, right? Restoring force will pull this to this point, hence tension. So check. Now, what about this? Again, this will expand. So let's let it expand. And once again, this is the final position. So restoring force will push it back here, which will shorten the bar. It's compressing the rod, rather, the copper rod. And we've already established copper rod is in tension. So this is incorrect. So once again, expansion is not happening here. Okay? So final answer, our change in temperature is negative. So let me show you what happens when we have a negative change in temperature, just to be sure. Okay. So negative change in temperature, that means our rod will shrink. Let's say this is the final position, right? There. Okay. And then this is how much it moved. Okay. There. As you can see, it checks out. This is the final position. Restoring force will pull it to this. This is deformation due to temperature. Restoring force will pull it to this final position. It's a pull. It's extending it, hence tension. Okay, so check. Now, what about the copper? So again, it's gonna shrink. So let's say it'll shrink this way. Now, also, the amount it shrinks is more than the brass, so we should exaggerate that. Let's make it significantly larger. So let's say this amount. Okay? And there. So that's the final position of your copper bar, and it started here. Okay? So this is how much it shrunk due to the negative change in temperature. And let's check. This is the final point. So as you can see, restoring force will pull it, will make it expand to hit this position. So again, expansion. So check. So indeed, this is a decrease in temperature. Okay. So as you've noticed, we're actually doing the first step in analysis for thermal stress, letting your object deform. Okay. So we remove constraints, we let it deform. This is what happened. Next step is to label your deformation. Okay. Once again, let's start with the deformation for temperature. That's easier. This is how much your brass bar deformed due to temperature. And this is how much your copper bar deformed due to temperature. And once again, this is the final position of your bar because it's free to rotate. So it can end up here. Unlike in our previous examples, right? This is a wall. It's always going to end up at that point. Okay. How about here? Right? This is a track. Okay. So there's a block here preventing it from deforming further. So again, it's going to end up at that point still as its final position because it's not free to rotate or deform. It's not free to deform that way. Same thing here. Again, there's two walls here. So at the end, final position after the restoring force is still at those points because there's no room to move. And same thing here. It was mentioned in the problem that there won't be any deformation in the wheel. Hence, the final position of your tire is still this. Okay, so this is what sets it apart from the previous examples. Here, it's not the same as the initial point. Okay, there's a different final position. Okay, and then let's figure out total deformation. Deformation for restoring force always starts where your deformation due to temperature ends. So here, towards the final position, which is here. This is your deformation due to restoring force. So delta PBR. Same thing here again. For copper, it starts where your deformation due to temperature ends. So over here. And then it goes towards the final position. So here. So that's your delta PCU. Okay, and those are your labels. Next step, create your equation. Okay. Now, to make things more obvious, let me do this. Okay. There. Okay. Now this kind of looks like one of our examples in the past topic, right? Where we have a bar, it deformed this way, right? And then we need a conditional equation. I think it's from your topic, indeterminate members, right? And the conditional equation came from the fact that we have similar triangles, right? This small triangle and then this large triangle. So we'll do that here as well. Okay, so similar triangles or simply by ratio and proportion. Okay, again, this came from similar triangles, side over side equals side over side. So let's start with the smaller triangle. Let me just write the dimensions as well. 3, 2, okay? So let's start with this. Let's start with its height. So this is the height. Can anybody give me what's the equation of this height? Looking at the drawing. Very good. Emmanuel and Emmanuel. Verse and Guico. Guico. 4 here. As you can see, this height is simply deformation due to temperature or delta T subtracted by this deformation due to restoring force. Okay, so delta TCU minus delta PCU over length, which is 3. And then equal to the corresponding dimensions for this larger right triangle. Now, can anybody give me what's the equation for this height? Correct, Cyrus. Very good. And correct, John Briones. Very good. Okay. As you can see, it's simply deformation due to restoring force minus that of temperature. So, delta P BR minus delta T BR, okay, over total length 5. Okay, and then I'll manipulate this equation. You'll get 5 times this equals 3 times this, right? Just multiplying both sides by 5 and 3. Now, you already know equations for these deformations. I'll just immediately write that here. Deformation due to temperature is alpha L change in T for copper, and then minus delta PCU. I know that. Delta PCU, we've solved for that. It's 3. Okay, so let's change these names to specify these are deformations due to restoring force. Okay, so that's 3, right, equals 3 times delta PBR, that's 1.8, minus, again, temperature, alpha L, change in T. Okay, now let's sub in the rest of the values. So 5 alpha, this is for copper, right, copper. Now let's see, alpha for copper is 16.8. So 16.8, that's micrometer. Once again, to convert micro to meter, times 10 raised to negative 6. L, total length of copper, that's 3. So this is 3,000. And then change in T is what we're looking for, right? Change in temperature to cause this. And then minus 3. And then equals 3 times 1.8 minus alpha for brass, 18.7. 18.7, again, that's micro, so times 10 raised to negative 6. Length, 2 meters, so that's 2,000 millimeters. Change in T. Okay, and then from that, you can solve for change in T. Please solve. What's the answer? Correct, Mariah and Gwyneth. Cavero de Guzman. Very good. Cavero de Guzman. 56.01 degree Celsius. Okay. And that's it for number 5. Do you have any questions for number 5? Please answer in the chat. Okay, no questions. Great. So again, I'd like to repeat, if you don't know how your system will deform, just make sure it's consistent with what's given and what you've solved for in the free body diagram. As you can see here, brass is given to experience tensile stress. And we've also determined copper also experiences tensile stress. So your material or system needs to deform in such a way to represent that. Okay. So another example, and the last example for this topic, number 6, also illustrates this analysis. So let's have that. Number 6. As shown in the figure, there is a gap between the aluminum bar and the rigid slab that is supported by 2 copper bars. At 10 degrees Celsius, delta is 0.18 millimeters, that's your gap. And then neglecting the mass of the slab, calculate the stress in each rod when the temperature in the assembly is increased to 95 degrees Celsius. And then for each bar, you're given the following properties. So again, let's analyze first. We have this slab and bar combination. The question is, what's the stress in each bar resulting from this increase in temperature? Okay, so that's basically it. So first, let's write the given. So at 10 degrees, let's call that your initial temperature, Ti. And then the gap was 0.18 millimeters. Next, final temp, 95. So Tf. Okay, and then next, the properties of everything. So let me just write that out. Area of copper, so ACU 500, modulus of elasticity is 120. Coefficient of thermal expansion is 16.8 micrometer per meter degree Celsius. And then for aluminum, cross-sectional area of aluminum was 400. E of aluminum is 70. And then coefficient of thermal expansion, 23.1. If you haven't noticed by now, E is always the same. Copper is always 120, aluminum is always 70, no matter the problem. Okay. And then another thing not given here, okay, but you can see in the drawing is that the length of your copper is 750 millimeter. So let's add that here. Length of copper, 750. And then length of aluminum is that 750 minus the gap. So we can solve for that. 750 minus the gap, which is 0.18. And that is 749.82 millimeters. Okay. All right. That's it. Also, to make our equation shorter later, we can solve for change in temperature right now. Instead of writing Tf minus Ti, I'll just immediately get change in T. And that's, okay, 95 minus 10, 85. Okay, so that's your complete given. Next step, same with your number 5, is to create a free body diagram and then equilibrium equations. Okay, so before we start with your free body diagram, we know that the system will expand, right? Okay, so you can either assume, is the expansion enough for this aluminum bar to hit the slab or not? So you can assume either. So I'll assume aluminum bar hits slab. Okay? And when that happens, you'll have this kind of free body diagram. Okay? Once again, forces. Let's start with copper. Copper is attached to your slab. Their bars acts the same as rods, wherein if it's attached, it will experience a tensile reaction. Okay? So tensile force away from your object. So I'm drawing it this way. Let's call that PCU. PCU. Once again, let's specify that as in tension. Tension. Now, what about the aluminum? Okay, aluminum, of course, acts here. Now, aluminum is not attached to the slab, and we've assumed it's going to hit the slab. So you can just imagine it as something pushing on the slab. So it's a pushing force, therefore it's towards the slab. So this way, let's call that P AL. And since it's towards the slab, that's in compression. Okay, so there. Those are our forces. Next, use equilibrium equation. There's only one that's beneficial to use, which is summation of forces vertical equals 0. Okay, so PAL minus 2 PCU equals 0. Now remember, the question here is asking for stress. So I'll rewrite P in terms of stress again. So that's simply stress AL, area AL minus twice stress CU, area CU equals 0. Let's sub in the values that we have. Area AL, area of aluminum is given, so 400. So you can write 400 stress in, or sigma AL, minus twice area of copper is 500, so twice 500, or simply 1000 stress in copper equals 0. Okay, there's nothing to solve for there, so you can just call that equation 1. Next. Okay, so again, similar to the process in number 5, the next step is to create another free body diagram to help in our analysis for thermal strain. Okay, so now we'll deform everything. Let me start. Let's say this is your slab. Okay, there. Okay. So in order to know how this slab will deform, again, you have to be consistent or follow what you have here. Okay, and then you have your aluminum over there. All right. So first of all, we already know this is expansion because we have an increase in temperature. So no need to wonder, is this a decrease or increase? It's given. Okay. So now, since that's given, obviously, this slab will move upward. Okay. Let's draw that. Let's say it moves this way. This is the new position of the slab. All right. There. Okay. So let's start now with your copper. Okay, take note the copper needs to be in tension. Therefore, the final position of your copper should be in a way that it's being pulled towards this edge. Now, why? Because copper is attached here. Final position would always be, for copper at least, attached to the bottom of your slab. Okay? So that means my copper will deform due to temperature just enough so that there's room to be pulled towards that edge. Okay, so this is how much your copper will expand. And again, restoring force will pull it towards this edge. It's a pull, stretching your copper bar, hence tension. So it follows. Okay, so let's just copy on the other side since it's the same material. There. Okay. And then this one, just to show it's being pulled here. Okay, its final position is this. There. Okay. Right. Now what about this aluminum bar? Okay. Our aluminum bar is in compression, so that means the restoring force is compressing it towards its final position. And again, this is the final position. Okay. So in order for our bar to be compressed, the expansion is always an expansion because it's an increase in temperature. It's gonna expand further than this edge because, so let's color that, so that the restoring force compresses it down to this edge. Okay, so there. Right. So that's your drawing. Next step, label. Okay, so this is the same as this. I'll just write it all on this side. Okay, this is our deformation. due to temperature in our copper bar. Okay? And also, this is the total deformation due to temperature in our aluminum bar. So TAL. Now for restoring force. This is the amount deformed by the restoring force. So delta P CU. And this is how much it deformed to go back to its original position by the restoring force again. So PAL. And then there's another thing given, the gap. So this is your aluminum bar original position. Therefore, this is the gap. Okay? And that's your delta. And that's all of your drawings. Next step is to create an equation. Okay. Now it's not as obvious as the previous examples, right? Where delta T equals delta P. There's a bit of a difference here, similar to what we have here. Now we won't use ratio and proportion here. There's no similar triangles, but just by looking at our drawing, you'll see that if I take this, right, total deformation due to length, and I subtract this and our delta, what I have is this height, which is the sum of my deformation for the copper. Okay, so that's my equation. Delta TAL, okay, this entire height, this entire deformation, subtracted by this, delta PAL, minus your delta, your gap, you're left with this height, which is this. Okay? So equals delta PCU plus delta TCU. Okay? And now let's just rewrite these equations. So this is alpha L change in T, and then I'll just do this to denote aluminum. Okay, this means values for aluminum minus, again, deformation due to force PL over AE or sigma L over E. I want stress, so I'll use sigma L over E. So sigma AL, sigma L over E. Again, for aluminum. Minus delta, which is 0.18. We know that. Equals, okay, again, sigma L over E. Now for copper, plus alpha L change in T for copper. And now we sub in the values. Okay. So alpha for aluminum, again, that's given 23.1. So 23.1 times 10 raised to negative 6 because it's micrometer. Times length of aluminum, we know that, 749.82. Change in T, we also know that, 85. Minus sigma AL, length of aluminum, again, that's 749.82 all over EAL, which is 70. So convert to MPa, 70 times 10 raised to 3. And then minus delta, which is 0.18 millimeters. So no need to convert, and then equals sigma Cu, length of copper, we know that, 750, all over E, 120, plus alpha of copper, 16.8. Again, that's micrometer, so times 10 raised to negative 6. Length is 750, change in P is 85. Okay, and then now we call this your equation number 2. Two equations, two unknowns. So using 1 and 2, you can solve for stress in aluminum and stress in copper. Okay, please practice solving simultaneous equations. What's the answer? Correct, Ralph? Gwensil? So for aluminum, okay, let me double check if I wrote things correct. Okay. Yep. 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 Okay, you might forget the point 18. Okay. Okay, correct. 16.73 for stress in aluminum. What about for copper? Correct, Ralph and Mariah. Buensil, Cavero. 3, 3. 6.70. I think if you didn't um, round off anything, you should get 6.6999. So 6.70. Okay, and then unit for stress, MPa. MPa, tension and compression. If you want a complete answer, aluminum is in compression. This is in tension. Okay, and that's it. That's it for number 6. Do you have any questions for number 6? Please answer in the chat. All right, no questions. Great. Since you don't have any more questions, I'll see you on Saturday, early dismissal. You may go. Goodbye, class.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
You're welcome.